Now, I will show you the specimen calculation for direct shear test. Let us say that mode of testing is disturbed and it is saturated. So, you should know what will be the molding moisture is equal to 20%. This is I am just showing some specimen calculation for direct shear test. So, you know that how to determine the moisture content, and C is molding density, and let us say 1.35 gram per cc. You know how to determine moisture content and the density. Now, you know that what will be the size of specimen in a small direct shear test, that is that is 6 centimeter into 6 centimeter into 2 centimeter. So, then you can calculate that what will be the area of the specimen. So, area of specimen is equal to 6 into 6, that means it is 36 square centimeter, and volume of the specimen is 72 cc. This is the volume of the specimen. Then you know the least count of strain dial, that is 0.01 millimeter, and then least count of vertical dial, that also 0.01 millimeter, and 9 is the proving ring. Constant, and that is 0.462 kg per division. So, from this we can measure that what should be the strain, what will be the vertical dial reading, that we can measure. And when you perform the test, you have to perform the test under different normal stress, generally 0.5 kg per centimeter square, 1 kg per centimeter square, 1.5 kg per centimeter square. So, you have to perform the test. Let us say this is the serial number, and you have to measure what will be the horizontal dial, that is in division. Then you can calculate the horizontal deformation that also in millimeter. You can measure the stress dial division, and then you can measure the shear stress, and that is in kg per centimeter square. Then you take the vertical reading and the what will be the axial deformation. Axial deformation in millimeter. So, you have to perform the test. Okay. So, this one, let us say all this is 0, 0, 0 and 0. Let us say 2 horizontal dial division is 30. So, horizontal deformation will be 0.3. Let us say stress dial division is 15 and the shear strength value 0.193, and this vertical reading let us say 1 and the axial deformation is 0.1. Let us say that serial number 3, when the horizontal dial division is 60 and horizontal deformation is 0.6, stress dial division is 27 and shear stress is 0.347 and vertical dial reading is 1. So, this is 0.01. I will show you one of the calculation that how we are determining. So, I will show for serial number 3 all these parameter how we have calculated. So, you know that horizontal deformation, this one. Okay. So, horizontal deformation is equal to horizontal dial division into least count. So, horizontal dial division is 60 and least count is 0.01, which I have shown you earlier. Least count is 0.01. Okay, this horizontal least count is 0.01. So, that means horizontal dial reading is this equal to 60 into least count I showed you 0.01. So, this will give 0.6 millimeter. So, that is why it is 0.6 millimeter horizontal deformation. Now, how to calculate the shear stress? So, shear stress, let us say shear, that is stress is equal to, that is stress dial division into moving ring proving ring constant, this divided by cross sectional area, cross sectional area. So, this will be equal to stage dial division is 27. So, this is 27 into that is proving ring constant, and this proving ring constant I told you that is 0.462 kg per division. So, 27 into 0.462, 27 into 0.462, this divided by the cross sectional area, and here is cross sectional area is 36. So, this is 36. So, this will be, calculate, you can have 0.347 kg per centimeter square. So, this is 0.34 kg per centimeter square. Similarly, vertical reading suppose 1, and then axial deformation, this is axial deformation for vertical dial reading 0.01. So, that is why it is 0.01. So, like this you have to perform the test and you have to take the reading for the horizontal dial reading. It may be 0, 30, 60, this it may be the 90, it may be 120, 150, 180, like that you have to continue. And I am just showing you that this is a different reading you are taking, like that you have to continue and take the shear stress value where you are having the maximum value. You can see here you can see that under normal division you are taking the shear stress value, almost maximum is here, that means 0.744 kg per centimeter square. So, this is the value we are having, but shear stress value under the normal stress of 0.5 kg per centimeter square. So, you have to perform the test under different normal pressure. So, when the normal pressure is 0.5 kg per centimeter square, you are having the maximum shear stress value 0.744. Let us see that from this table we can write that when the normal stress that is sigma n is equal to 0.5 kg per centimeter square, then you are having the maximum shear stress, okay, is equal to 0.744 kg per centimeter square. So, under this normal stress you are having the shear stress value. Similarly, you have to again apply the normal stress. Let us say normal stress sigma n is equal to 1 kg per centimeter square, and then you can determine what should be the shear stress, maximum shear stress value. So, you can have the maximum shear stress value. You can see here that when the normal stress is 1 kg per centimeter square, and then you are taking the reading and you are determining the shear stress as you have done in case of normal stress as 0.5 kg per centimeter square, and for 1 kg per centimeter square you are having this maximum shear stress value 1.052. So, similarly, when the normal stress is 1 kg per centimeter square, you are having that shear stress value is 1.052 kg per centimeter square. Now, if the normal stress, that is sigma n, is equal to 1.5 kg per centimeter square, 1.5 kg per centimeter square, and then you have to determine what will be the shear stress. So, you can have that when the normal stress is here 1.5 kg per centimeter, then you are taking the reading, the shear stress value, you can calculate it, and then you find what should be the maximum shear stress, that is 1.18. So, this shear stress value is 1.18, this is kg per centimeter square. So, what you are having from this direct shear test, under the different normal stress you are calculating that what will be the shear stress. When the normal stress is 0.5 kg per centimeter square, then shear stress 0.744 kg per centimeter square. When the normal stress is 1 kg per centimeter square and shear stress value is 1.052 kg per centimeter square, and when the normal stress is 1.5 kg per centimeter square and then shear stress is 1.18. Now, we can plot the graph in between the normal stress and the shear stress for the determination of the shear strength parameter. So, I am showing that what should be the normal stress and what should be the shear stress value. So, here you can see the figure, this is the normal stress and this is the shear stress. So, we know that when the normal stress is 0.5, when the normal stress is 0.5, then shear stress is 0.744. That means, when the normal stress is 0.5 here, and then this shear stress value is this one, when normal stress is 0.5. So, you can plot this point. Okay. When the normal stress is 1 kg per centimeter square, shear stress is 1.052. That means, when normal stress is 1, then shear stress value you are having 1.052, this one. That means, you can have a point somewhere here. When the normal stress is 1.5, shear stress is 1.18. So, when normal stress is 1.5, then shear stress value is 1.18. So, you are having a point here. So, you are having 1, 2, 3 point, then you draw a line which you call the mode failure envelope line, and this angle is equal to pi, and this intercept, this is what you call the cohesion. So, you can measure the cohesion, which is C is equal to 0.556 kg per centimeter square. You are having angle of shearing resistance pi is equal to 23.5. So, from this direct shear test, so you can determine what is the normal stress, what will be the shear stress value. So, if you know the shear stress and the normal stress, So, you can draw the failure envelope, and from this failure envelope you can determine what will be the angle of shearing resistance, that is pi, and here pi is equal to 23.5 degree centigrade, and the cohesion intercept, that is C is equal to 0.556 kg per centimeter square. This is what is called the shear strength parameter, and this parameter is very important for design for any infrastructure in geotechnical engineering. So, we should know how to perform the test, direct shear test, and how to calculate the shear stress under the different normal stress, and then you can determine what will be the shear strength parameter, that is C and pi. You can also determine the vertical deformation and the load, and that also you can plot to determine the displacement of the soil. Now, you can also plot the horizontal deformation and this is the shear stress. So, you know that horizontal deformation from this table, you know that what will be the horizontal deformation under different load. It may be 0.5 kg per centimeter square, 1 kg per centimeter square, and the 1.5 kg per centimeter square. So, under the different normal stress, you can determine the horizontal that deformation. Let us say here this is the horizontal deformation. Okay, this, let us say this is the horizontal deformation under the load of 1.5 kg per centimeter square. This also like this also you can also see also the earlier that what should be the, this is after 1.5 kg per centimeter square, what will be the horizontal deformation. Similarly, for the 1.0 kg per centimeter square, 1.05 and also 0.5 kg per centimeter square. Like that, from the different loading, so you can determine the horizontal deformation. So, this is the horizontal deformation in the x axis and the shear stress on the y axis. So, under the different normal stress, so you can plot the curve in between the shear stress and the horizontal deformation. So, this is the under normal stress of 0.5 kg per centimeter square, this is for 1 kg per centimeter square, and this is for 1.5 kg per centimeter square. So, you are increasing the normal stress and shear strength value also equally is increasing. Now, there are different types of the test, and if it is a unconfined compression test. So, in case of unconfined compression strength, that is Q, is the load per unit area at which the cylindrical soil specimen fell in compression. It is the twice the cohesive strength or the undent shear strength for saturated clay. Let us say this unconfined compression test. Let us say this is unconfined compression test. So, there is no confinement. Okay. So, unconfined compressive strength which can be designated at Q of U. So, this unconfined compression strength Qu is equal to P divided by A, where P is axial load, A is corrected area, and this corrected area will be equal to A of 0, this divided by 1 minus E L, where A0 is initial area, and EL is axial strain. So, you need that correction of the area. So, you will be knowing what will be the initial area of the sample, and also you know that what should be the axial strain, then you can determine what should be the corrected area, that is A will be equal to A0 divided by 1 minus EL. So, for this kind of the test also it requires some apparatus and the accessory required. So, machine driven mechanical load frame capable of providing the speed in the range of 0.5 to 4 millimeter per minute, because rate of speed is very important in case of this kind of the testing. Unique providing ring of capacity 1 kilonewton and accuracy of 1 Newton, platen with the axial strain dial gauge, mounting designed for the unconfined compression testing. Then dial gauge of least count of 0.01 millimeter, lever assembly filling to the dial gauge, apparatus for extruding and trimming the undisturbed soil specimen, and vernier caliper, balance and drying oven. I am showing you what are the that equipment is needed here. This one is the vernier capillary, this one, and this is the dial gauge here, dial gauge which you can measure. Then this is the drying oven in which you keep the sample for drying, and this is the weighting balance. You can weight the soil specimen, and this is the sample extruder in which sample is to be extruded from the mold for the testing. And here also unconfined compression test, this is the test assembly, and here is the soil, you can see soil specimen, here is the moving ring, and this is the reaction frame. So, this is the soil sample, this is the unconfined compression stage, and you can see this is the soil sample is here, and you can apply the load at a particular speed, and then you measure what will be the unconfined compression strain of the soil. So, because it is a unconfined compression test, so there will be no confinement effect. So, only you can determine what is unconfined compression strength of the soil. This also parameter is very important. So, this is also one of the simplest test in which you will be knowing that what should be the unconfined compression test of the soil sample. Thank you.